Okay, I think it's well 3 o'clock local time here, and wow, uh, so I see we have a nice crowd. First, let me confirm: am I being heard? Okay, can you all hear me? Or some of you hear me? Right? Is the audio okay? Okay, good, excellent. Okay, I like that, and good. And my screen share. So. I hope you can all see the screen share. And is the visibility of the presentation that I'm kind of scrolling through now a little bit? You can all see that? Okay. Okay. Very good. Okay. Excellent. And okay. Um, so yeah, the Zoom is nice, although I still prefer a room with people as opposed to a matrix of black squares. But okay, good. And I want to thank the organizers for putting this together and giving me a chance to speak to you. I'm looking at my chat. I'll try to relate to that, although I'm also not that experienced with it. So someone can interrupt me if I'm not paying attention to a question that needs to be answered. But okay, so this is machine learning for deep learning for dummies. I'm Aryeh Weiss. My collaborator on this is Ann Allerding, who provided most of the images and is the person who is researching soybean plant productivity. So for a change, it's not microscopy, although at the end we'll get to at least some images that needed to be acquired in a microscope. So that's what we have, and I'm well qualified to give this talk because I just started doing this kind of thing about a year and a half ago, and I'm going to describe my journey. I'm one of the dummies, basically, and I say that in all seriousness, and I'm hoping that hearing about the journey I took to be able to implement a deep learning application will be of use to some or all of you. So therefore, I'm going to really start I'm going to be describing a problem involving the segmentation of soybean plants. And you see a picture of a soybean plant here. I'm moving it a little bit so that it'll hopefully get your attention. I'm viewing this on a 4K screen, so it's not quite sure how well you're going to see it on your screens. I hope that you will be able to see it with a good enough resolution. But these are a bunch of plants you can see, and these are de-leaved soybean plants. And there's an interest in being able to extract data concerning the productivity of the plant. And that's because soybeans are a big, big industry, at least in the United States. So I will start off with what I was doing with what I call classical image processing. And classical image processing is what things like using ImageJ or other such programs to use maybe do a histogram analysis or run through different filters to identify features of interest. And that was my starting point. I had a good deal of experience with what we call classical image processing. Then I'll talk a little bit about what I call shallow machine learning, which is a way of basically feeding the computer a lot of features and having it somehow analyze, cluster those features and do some kind of segmentation for you. And then I'll discuss the deep learning that I moved to, and we'll see why that happened. One thing that you're going to see is that when you go to deep learning, it doesn't mean you abandon classical image processing. You take the best of each idea to do the work. So in classical image processing, a typical workflow is to do some noise reduction, background leveling, some kind of pre-processing. You do some kind of filtering that enhances the objects versus the background. Maybe you'll do an edge detection or maybe some kind of morphological process. Then typically, once you've enhanced the objects, you do a thresholding operation and you find, you separate objects of interest, and then you do some kind of analysis. You look for all the objects that are round, have a certain size, have a certain brightness, and so on. And that's good. And an example of that is when I wanted to identify the plant against the background. It's not a difficult problem, but it turns out that there are subtleties here, and each plant, where the lighting's different or the morphology is a little different or other artifacts occur. And it took I had to write a program in Python that ran under the Fiji implementation of distribution of ImageJ, and you see the result. Okay, the result is a segmentation, and that's the plant. And I actually drew edges around it so that, to show that the original plant was really segmented nicely, and that was very good. But, and there's always a but, the but is that I wanted more. We wanted to find the soybean pods as opposed to the stems. So first, how does this kind of segmentation work? Well, it's a color image. So we did it in a color space, the lab color space. Once we went to the color space, we saw that that green plant or whatever stood out against the background. We thresholded. We used some size criteria to get rid of artifacts and garbage. And this is an example of a conversion to a lab color space. And you can see that there's a luminance, the A channel and the B channel. These are, this is a color space, basically. I can't tell you that the A channel is red and the B channel is blue. I can just tell you that the colors can be separated into these two channels. And you can kind of see how in the B channel, you kind of get a nice contrast for the plant. The A channel, you also get a nice contrast, except at the bottom where you see that the stem, the main stem, actually has a reversed contrast, and and then you can use the luminance channel also. So that was nice, and that's a typical example of classical image processing workflow. But the problem is, how do I segment the stems from the pods? Now, you look at it and you say, well, the pods are thicker than the stems. Well, yeah, but, near the bottom, the main stem is pretty thick. Say, well, color. Well, yes, but it turns out not quite. And we tried that. I tried playing, finding features that would segment those pods. And here's an example of a heat map of thickness. And you look at it and it looks promising, but it turned out that it didn't really do the job for us. So we had a problem. How are we going to segment the pods from the stems? And that's where machine learning comes in. So we started with what you'd call shallow machine learning. Okay, in shallow machine learning, you're basically saying there are a set of features that distinguish pods from stems. So I'm going to measure a whole mess of those features, a whole lot of them. It's really like regular machine learning, except maybe I'm not quite bright enough to see the 2 or 3 features I really need. So I'm going to, measure 10 or 15 features, and I'm going to put that into a program that knows how to cluster those features together, and it'll find clusters, and it'll say, oh, it looks like this cluster is pods and this cluster is stems. So, and this cluster is background, for example. So that's typically how a shallow machine learning might work. And one of the reasons I can do this is because people have written programs to enable me to do it so that I don't have to write it myself. So a program like Ilsastik, lives for the purpose of doing this kind of thing. And I'll show you an example. And in ImageJ Fiji, you have for a long time trainable Weka segmentation, TWS, and it's a nice plugin that also was written already many years ago and developed. And you can use these to tell it, measure a whole bunch of features and try to do some kind of clustering for me. So this is an example of, training in machine learning. And this is a screenshot, well, a window shot from Ilsastik, where you select the features. And I just, selected them all because I got a computer with a lot of memory and I can do this. But you can see these features are not all orthogonal. I mean, they're not all independent, but you have intensity-based features and edge-based features and moments, different moments, texture-based features. And you get all these things together. And this is an example of how you train it. I don't know if you can see this, but you see there's like a red line here and a red line here and a green line on the pod and a green line on the pod. And this is very sparse annotation. And I'm basically telling the system, this is a pod and this is a stem. And because I know that the main stem at the bottom tends to be problematic, I make sure to label that and tell it that's a stem. And here's a stem and here's a stem. And when I do that and I tell it, okay, now try to find all the stems and pods for me. And this is what you get. And the red are the stems and the green are the pods. And that looks promising. And this was very little work. This was done in Ilsastik. You can see all kinds of artifacts around the edges here, but they don't bother me because you remember, I know how to find the plant. So I don't really care if there's all kinds of artifacts in the background. I can mask the plant against my classical segmentation. So you see these things can work together. Okay. So, and here's an example of applying this training to a naive image, an image that wasn't annotated. It looks okay, but if we were to look closer, we would see it's not really good enough. I mean, it does find the pods, but a lot of the pixels on the pods are misclassified, so it doesn't really measure the pods that well. It's got misclassifications on the stems, and it turns out that in order to get it to work well, I have to do more annotation. When I do more annotation, it takes a lot longer to train, and it tends to be a very good thing for use within one class of plant. Like if I annotate this plant, it'll do this plant pretty well. And that's also not bad. Very often that's exactly what you want. You take a microscope image and you mark a few cells and then it finds all the cells for you. So it can be very good. But in this case, I wanted it to be able to work on many dozens of pictures, and I didn't want to annotate them all. So it wasn't quite good enough for me. And yet we did get nice results with it. And I think we even presented it at a conference on plant biology. And it's a very good thing. And it's a tool that I recommend that you take a good look at. And there are, with all these tools, there are many online YouTube videos and things like that to show you how to use them. And the people who wrote them have invested a lot in making them usable. It's really an amazing thing. So, okay. So that's our shallow machine learning. So I call that shallow just because the other, neural networks are deep machine learning, but it provides a convenient tool for high dimensional feature spaces, right? I got, measure 31 features and cluster them. It provides pretty good results with relatively little annotation, relatively little work. It requires a prior selection of a feature space. You have to know what features you want to look at. I mean, if you don't know, you could select 30 different features, but in any case, you're selecting a feature space. And when it works for you, it's very simple to use. It'll work on regular computers. You don't need a GPU to make it work, graphics processing unit. And that's good. That's good. But we wanted more. And the title of the talk was originally Deep Learning for Dummies, until I saw that I was going to also say something about shallow machine learning. Then I made it machine learning and deep learning for dummies. So we'll get to the deep learning, because that's what I spent the most time trying to learn, because I didn't know it. And all right, so I'll say a few words of introduction about deep learning, but I'm not really going to give a tutorial on deep learning, because I'm really going to talk about the way I marched through some tools that allowed me to do it without having to really be an expert at it. But what is deep learning in any case? So it's based on neural networks, and we'll define that in a moment in case you're not familiar with it. The thing about the deep learning approach is that it finds the features as part of the training. In other words, you don't know ahead of time, and often after the fact, you also don't know what were the features that it used. There's some interesting work from a group in Ben-Gurion University. I forget now the name, but they took a deep learning approach to analyzing mammograms for, breast cancer tumors. And then they had an approach that caused the deep learning system to emphasize the features that it used in order to make the determination, so that you could go back and see what were the features. But generally, you don't know the features. The network kind of magically figures it out. And we're going to see these networks might have, 50 million parameters. So you don't really know exactly what it was that it saw. Okay, it's computationally intensive. Did I say 50 million parameters, right? It's computationally intensive, especially for images. There are free and excellent Python libraries that have been highly developed and are available for doing it. TensorFlow and PyTorch are two of them. There are prepared programs like ZeroQuest, DL4Mike, and at some point I have a GitHub site that at some point I'll put this presentation on, so that you can also see the links. But like ZeroQuest ZeroQuest Deep Learning for Microscopy, and you'll find there a whole set of examples that are designed to run on Google Colab, which do different types of microscopy things: 2D, 3D, semantic segmentation, classification. And I'll define semantic segmentation in a moment. Okay, there are GUI tools. You don't even have to know how to program. I mean, for these, you got it. But mianalyzer, I'll talk a little bit about that, because I started using that and it helped me a great deal. And then ironically, I went and wrote code in Python to run it because I needed to do that. MATLAB Deep Learning Toolbox. The MATLAB Deep Learning Toolbox is not free. Okay, that's the downside, but it is very powerful. Most of the tools I talk about here are free, and you can just start learning how to use them. It usually requires a large training set, and we'll talk about that. You need a training set. That means a set of images that you have marked, annotated to, I mean, there's also such a thing as unsupervised machine learning and so on. I'm only talking here about supervised machine learning. That's all I've done, and that's all I'm talking about here. So that's what deep learning is about. Now, just a little word, neural networks. That means you put your data in. In the case of images, these are pixels or parts of images. You have interconnected units, which are kind of modeled after neurons, which is why they're called neural networks. They're interconnected, and you have a lot of connections here. There are hidden layers in here that you don't even see. And then out magically comes your prediction. And when you want to segment an image, what has to come out as a label is an image whose pixels are labeled. The way this works is, well, the predictions come out, they go into a box which is labeled here as loss function. What that means is you put the real answer into the box, you put the prediction in the box, you get an error out, because when you first start, it has no idea, right? You get an error out. that goes into some kind of learning algorithm that fixes up the parameters, and then you do it again, and you do it again, and you do it again. So you go through a set of iterations, epochs, and let's say 50 epochs. I once ran a program where I needed like 1,000 epochs, but in any case, you go through these iterations. Each time we hope that this is going to convert, the error will get smaller and it will hopefully converge. That's the whole idea of the neural network. You easily have millions and even tens of millions of trainable parameters here. And so you need some serious computing power, at least for the training. Once you've trained it, it's not difficult to use it, but you need some serious training. That's a neural network. Now, if you were to just put an image into this neural network with 1 million pixels, let alone, 5 million pixels or 10 million pixels, and then you started interconnecting all the pixels with all these units and so on, you'd get something that was completely unmanageable. So once again, people, very smart people, figured out how to do this reasonably. The two words that you're going to hear a lot, and that's why I'm going to mention it, are convolutional neural networks, which means you have layers that do convolutions. Now, what is, one moment. Okay. So what is a convolution? Okay, that's from standard image processing. So I hope that you'll be familiar with it. But in any case, a convolution is an operation where you take something like a kernel and you, well, I don't know, I won't define it now, but convolutions are able to be run fairly efficiently. And what you'll get out from them is some kind of map of properties. And just to give you an idea of what that means, I'll just take this blobs image. Let me make it bigger. Okay. And let me run a convolution on it just to show you what that might look like. Okay. So let's try doing that. Okay. So here's something that you'll see in a moment what it does. Let's preview it. Okay. So what this is going to do, what is here is called the kernel. You may not be able to read it, but it's a set of 9 numbers, 0, -1, -1, 1, 0, -1, and 1, 1, 0. And it will emphasize diagonal lines of a certain orientation. And there you go. You can see that now this image is left with a bunch of diagonal lines. Okay. And I could open a different, let's see if this is the one here. So this is a different one. And now we'll see a different set of diagonal lines. You see? So these convolutions give you a bunch of properties. So you might have like 64 convolution layers, and that will give you a map of 64 different properties of the image. It's got diagonal lines here, and it's got horizontal lines there, and it's got spots over somewhere else and stuff like that. And the point is it's fast. And the other thing that you may hear sometimes is UNet, and that's an architecture, a neural net architecture that happens to work nicely on segmentation of images. And this is what a UNet looks like. And here you've got 64 convolutional filters, and now you downsize and downsize and downsize and put in more filters and more filters. And then somehow by magic, you upsize and upsize, and out comes a segmentation. And please don't ask me, I couldn't possibly implement it, and I couldn't even explain all the details of the network. But this is a network that apparently works very nicely for segmenting images. And the point is that it's again implemented for you. So it's called the UNet because it kind of looks like a U. And then there are a bunch of variations of UNets. There are a lot of variations of these things, and we'll talk about that in a moment. So let me take this off now. You've seen what the plant looks like. And so why can we do it? I mean, this is complicated. It really is. I couldn't program my own UNet. How could I do it? Well, we can do it because there are many free software tools available: TensorFlow, PyTorch, mianalyzer, deep ImageJ, microscopy image browser. I'll say a few words about that at the end also because it's the support for it is absolutely amazing. We have serious computing power available now. Half a year ago, I had to run the training sessions on a remote GPU cluster, and I could do that. That's the reason why I had to write a headless version of mianalyzer, something that would run in Python. But now I can run it on my laptop because my laptop has an NVIDIA TI 3080 16 gigabyte with 16 gigabyte of RAM. The GPU cluster, its GPUs only have 12 gigabyte of RAM on it. Of course, it's got a lot more cards than mine, but still, I think that's pretty amazing. And it wasn't really that expensive a laptop. I mean, you know, it was something that we can afford. So, of course, the laptop does get pretty hot. If you're going to do this on a laptop, get a cooling stand and maybe an external fan besides, because it's going to run hot with this thing. But it's still pretty amazing. And so that's the second reason. Online tutorials and free courses are available. You just Google on TensorFlow tutorial, PyTorch tutorial, and you will come up with a wealth of things that are out there. Courses and just people who, out of the goodness of their heart, you know, give you, put this stuff up. And most important, and I put this because in big, bold letters, there's an incredible community of developers and users who provide help in close to real time. And I really mean this. There's the ImageSC forum, and under that, let's say the tag of MIA is for mianalyzer and MIB is for the microscopy image browser, and so on. And I get answers on there, you know, an hour after I put a question up, sometimes minutes after I put a question up. Not only that, but, you know, I had this microscopy image browser analyzer, and we're going to talk about the type of training data it needs. And it needs this thing called NPZ files, which I'll talk about in a little bit. And I didn't know how to make NPZ files. What I know how to make are label images that look kind of like this. This is in false color. And, you know, the background is 0 and the blue is 1 and the red is 2 and the green is 3 or whatever. And I don't know how to turn this into an NPZ file, but Niels Korber knows how. He wrote mianalyzer, and he sent me a Python script that does it. And then I modified the Python script and made it a little bit more for, you know, useful for me and so on and so forth. But the point is, he did that for me. And then I was able to set up my label images for mianalyzer. MIB, microscopy image browser, I was having some trouble with it. And the lead author of it, Ilya Belovich, spent 2 hours with me by Zoom, you know, doing all kinds of things and giving me good ideas besides. So I can't say enough, stress enough, how important this is. And the same goes with Fiji ImageJ, and the same goes with QuPath, where I needed a macro, and we're going to talk about that in a little bit. So, you know, I really can't say enough about that. So where did this all go? Well, this is kind of a summary of what happened. Here's my plant, and here's my segmentation, and it's pretty good. I mean, you know, the bottom of the stems all came out right. The stem is correct. The pods are correct. Now, at present, I haven't really quantified it, but I've done a lot of these images, and they just by eye, they're very good. I mean, you see the pods are the pods and the stems are the stems. There's some background artifacts that you see, these lines, but that's okay because we know how to mask the plant. No problem. So this is an example which was trained on UNet. The backbone is EfficientNet B1. Oh, what's EfficientNet B1? Well, mianalyzer has like, I don't know, 20 different architectures or backbones that you can try. And I've tried a lot of them. And again, it's just graphic user interface driven. And so it's very easy to do. I've got 4 classes here: the pod, the stem, the background, and also unlabeled. In other words, I don't have to do a complete annotation, although we do annotate a lot, but it doesn't have to be fully annotated. This was trained for 100 epochs. I think the training took about an hour, maybe 45 minutes. And I was using mianalyzer. Okay. So how did we do this? So here's the workflow of pretty much any kind of deep learning problem you're going to have. You got to prepare a training set of representative images. Okay. You need to annotate the images. And this is an example of an annotated image. Okay. It's not fully, you can see that there's parts missing here because it's not fully annotated, but that's okay. What's annotated is annotated, and what isn't is ignored. So this is an annotated image. This is another example of an annotated image, which is done a little bit differently. It's fully annotated. That is to say, the stems and the pods are fully annotated, and then the background is just the 0. Okay, you must have an annotated image set. This is a bottleneck. Okay, it takes time to annotate images, especially if you're doing semantic segmentation, which means if you want a pixel by pixel segmentation. Okay, so you must convert the annotated images to the correct format. In the case of mianalyzer, it's NPZ. A lot of programs want this 0, 1, 2, the kind of images that I showed you. You then train, test, and predict. Okay, train, test, and predict. That's the easy part. I mean, once you've got this is the hard part, getting yourself an annotated set. So how do we do that? Well, there are a lot of tools available for annotation. There's something called Label Me. ImageJ Fiji can be used to annotate. You can make regions of interest. QuPath, I'll talk about that because I use QuPath. QuPath does a lot more than annotation. I mean, there's a talk about QuPath later today, and I'd recommend you check in on that. QuPath does a lot of stuff. I used it for annotation. I hope that the author will forgive me for taking his big, powerful package and just using it to annotate my images. But the labeling is basically manual, but there's some semi-automatic tools like the magic wand. And just to give you an idea of what that might look like, a little preview. So here is QuPath, and I'm making this image larger just to show you what a magic wand tool might do. So here's a pod, and watch what happens as I try. Whoop, that's not exactly what I wanted. Let's get this right. Wait a minute, that's supposed to do that. So there, you see? So I just clicked on it, it filled it in for me. Now, of course, it doesn't always do such a great job. And there are ways, QuPath has a nice tool for, let's say that, let's say this shouldn't be, so see, I can take that away. But that magic wand tool, that ability to click on this and just have it, fill something in like that. See, that. Okay, that is nice. That is really nice and very helpful. And that's the reason. That's the reason I use QuPath, is because its tool. Let me just get rid of this now. Its tool is the one that worked best for me. Although there are other tools that have similar capabilities. Okay, so that let me just show you that. Okay, so let's say that I think that okay, see, so I just clicked on it and it moved to the edge. It moved to the edge. So that's the reason that I use it, and that's what you end up with. That's what the segmentation looks like. Now, okay, that's a magic wand. Semantic segmentation is where you want to classify every pixel. It requires fewer images, because if you look at an image like this, you'll see that there are tens of thousands and hundreds of thousands of pixels. Each of that is a training data point. So you can get really decent results training with 5 or 10 images. I've got 30 images that are annotated, but you know, you get really nice results even with 5 or 10 properly labeled images if those images are representative of the classes of images that you want to see, that you want to segment. But the annotation is harder. It takes a lot of time, even with good tools, to annotate these images. Okay. Now, instant segmentation, that's where you may want to classify objects or images. And that's not what I'm doing today, but I did want to mention it because we are starting to do it. We're looking into it with the plans also. In instant segmentation, you may want to say, or that's a classification, like these are digits from the MNIST digit database, handwritten digits. And this is an 8, a 1, a 5, 1, and so on. We don't care if this pixel is in the 8 or not. So we're not doing a pixel level classification. Okay, we're not doing that. Instead, we label these simply by saying, okay, the ground truth is this is an 8, this is an 8, that's a 1, that's a 5, and so on. That's pretty easy to do, right? You've got 10 classes, 0 through 9, and you can just go by and, you know, even mianalyzer has a nice little tool to do that. You define your 10 classes and you put your images up and you just click a button and say, okay, that's an 8, that's an 8, that's an 8. That's easy. But you need a lot of images. I think the NMIS database has 60,000 of these images. You need a lot of images in order to do this classification and get it right. So, and the output of your neural network in this case will be one of 10 possibilities. And you'll get a set of probabilities that say, okay, this is most probably an 8, but maybe there's an 80% probability it's an 8, and maybe a 15% probability it's a 7, and, you know, 5% that it's something else. Because this one looks a little bit off, you know. So those are the 2 kinds of segmentation that, you know, there's other kinds also, but those are the 2 kinds that I've been dealing with, and mostly I've been with semantic segmentation, and mostly using semi-automatic labeling or manual labeling with QuPath. That's what I've been doing. And this is just a static slide that shows it in case the dynamic display didn't work. But this is the reason I use QuPath. It has a convenient magic wand annotation mode that works nicely. And also, it has a nice scripting ability. And the QuPath, you know, after you've got these annotated images, you've got to turn them into, you know, label images where this is a 0, that's a 1, that's a 2, that's a 3. And it turns out that you can do that in QuPath easily with a script. Let me see if I can find it. One moment. Yeah. See, that's a script. Oh, don't, you know, it doesn't matter how well you can read it. This is a groovy script, which is Java-like, I guess. And this is a script that saves my annotated images as labeled images, with the background being 0, the background being 1, the pod being 2, the stem being 3, and the unlabeled, which it also calls background label, being 0. And again, I did not write this script. I modified it. This script was something that I found through the ImageSC forum, right? I don't remember who gave it to me or who pointed me to the script, but then I modified it so that it would, you know, handle my labels and my classes and so on. And that's kind of highlighted here in the yellow. So that's the lesson, really, is try to do it. And if you don't know how to do it, ask on the forum, because someone's going to know the answer to your question. So good. So now I've got these labeled images, and I go to mianalyzer, and I want mianalyzer, and here's the user interface for mianalyzer, and I've zoomed it up a little bit so you could see. And here is my training set, and it is smart enough to know that I've got images and I've got labels. And the reason it knows I have labels is because, if I can find it, yeah, I have to open up a new window. The reason it knows I have labels is because, hold on a second, is because the labels must be in a specially named subdirectory called segmentation labels, and it knows to look there. So let me show you that. New window, and here is, oh, let's look at this guy, and let's look at my annotated images, and let's try training from predicted and segmentation labels. And if you look at segmentation labels, you see a bunch of files in here that end with NPZ, and it's not important if you can read the file names or not. And every one of those NPZ files corresponds to an image file here with the same name. And I guess one of the lessons here is that for every one of these programs or packages, you need to know where it wants to find the data and then set it up accordingly. All right. So, but again, the question is, let's go back to these files. How do you get the MPZ files? Well, if you open an MPZ file, what you find out is it's actually a zip file. It's a zip file with a whole bunch of NumPy. Okay, NumPy is a numerical package for Python. NumPy arrays, and those NumPy arrays are actually contours. And those contours describe the labeled image. Now, how do you convert the labeled images to contours? And again, the way you do that is, let me see if I can even find it. Oh, okay. One moment. The way you do that is with a program, which, let's open one of these guys up. Let's open a new window since I forget where I put the other window. Okay, so let's run code for VS Code. And we're not going to actually run this, but we'll look at it. Visual Studio Code. And I'm sorry that I still haven't figured out how to get the font here by default bigger. But in any case, what I really want is to just show you. Let's open a recent thing. And let's see if we can find it. Convert. There we go. Yes, I do. Okay, so here's a Jupyter script. And gee, I wish, yeah, I don't remember how to make the font bigger. I apologize for that, but it's not, you don't have to read the code. Point is, here's some code. And the code this code will read a bunch of label files and will convert them into NPZ files and write them out. And it was written, as I said, it was written initially by Nils Korber, and I modified it a little bit just to work and find my directories and stuff. And again, so I put a link in here for mianalyzer. Okay, so I'm going to describe my workflow based on mianalyzer. So here it is. This is the same graphical user interface that I'm showing you here, right? The only thing, this one I can actually change pictures. And what you can do with this thing here, this is a menu, and you get to choose your architecture. And here, again, you don't have to be able to read them, but ResNet 50 and Ceresnex 101 and EfficientNet B0 and all these things. And you could Google if you want to know what these backbones actually are, but they're all architectures for neural nets, and you can select them just by a click of the mouse. And then it says, okay, my images are colored. I've got 4 classes. I have a certain batch size. If I make it too big, I'll run out of memory because 16 gigabytes just doesn't go as far as it used to. Says the guy whose first computer program was written on a mini computer with 32 kilobytes of memory, of core memory. Most of you probably don't even know what core memory is, but once upon a time. And you select your various properties and you can train. That's what you do. I won't try to train now because if I do, my Zoom will probably collapse because it really takes a lot out from the computer. Okay, so but that's what it looks like. That's what it looks like. Now, So I mentioned about labeled images and NPZ files. And so I already showed you that I had a Python script to do this. And I have a GitHub site where I have that multi-class conversion script sitting. So, you know, again, when I eventually I'll post this thing, but if you just look for GitHub Aryeh Weiss or Aryeh W or something, you'll find my GitHub page and you'll find the directory for this. You'll find a repository for MIA headless. This MIA headless thing, okay, I'll say a word about that. But just to summarize, the labeling workflow was to annotate in QuPath, save the annotated images in pixel labeled images, and then convert them to NPZ files. That's the labeling workflow. And that's really the bottleneck in almost every deep learning problem, any machine learning problem practically, but deep learning especially. And after that, train, predict. I mean, there's a button here to push to train and predict. Let me see if okay, I'll say a word about the remote operation. When I first started doing this, I couldn't train on my laptop. So I needed to do it on a GPU cluster. But this is an X program, an X Windows program. And running the user interface over X from my home was painfully slow. I mean, it really was not, it was often not doable. Okay. It took too long. It would time out. So I couldn't run this thing using the GUI. So I needed a way to run it headless. And let me see if I can find it for you. Okay, open recent. Let's see if we got it. Oh, I don't know if I have it in my recent things. So anyway, no matter. It's a Python script. And what happened is that Nils Korber wrote me a minimal Python script that could do the training, okay? And then because it's open source, I went into the open source library, and unfortunately there isn't a well-defined API for it right now, but I looked at the various functions, I figured out what they did, and I expanded the script to be able to read in the images, train them, and then do a prediction, basically to run the workflow. Can't quite do everything the GUI does, but it can do a lot of it. And that's called running headless in remote operation. And that's how I trained models initially before I had the laptop with a good GPU, because my old laptop only had 4 GB RAM on the GPU, and that's not enough. You need at least 12 GB, and I've got 16 now. And nowadays you can buy the laptops with 24, and it's really amazing. So I'm using a Lenovo P1 Gen 5 Extreme laptop computer, and I can do the training. My training can be done on it. No doubt in 3 years it won't be good enough, and I'll need one that has 64 GB, whatever. Okay, so that's what I wanted to say about remote operation and the results. And now here's results with EfficientNet V1. What's EfficientNet? Well, it's an architecture that someone came up with that it was, apparently is one of the latest and greatest things, and works. And I found that it works very nicely. All the EfficientNets, B1, B2, B3, and you can, I keep Googling them to find out exactly what they are, and then I keep forgetting exactly what they are. But here you go again, another one, and another one. And these are all different harvests, different plants, and so on. It works very nicely. It works very nicely until I look closely and I find out that because these were photographed without fill flash, there are shadows that sometimes get picked up. And I'm working on that now to redo the annotations to make sure the shadows are annotated as background so that I can retrain it and have it know that the shadows are background. But okay, and you can just look at it and see that it works nicely. But what if you want to do more than look at it? Well, to evaluate results, the two of the metrics, there are a number of metrics, but 2 of the metrics are intersection over union or dice coefficient. They're more or less similar things. intersection is the intersection between the predicted and the ground truth. Ideally, of course, it will completely intersect. And then this is the union between them. And in an ideal situation, the prediction is exactly the ground truth, and this is just one. Similarly here, in an ideal situation, it's 2 times the intersection. And in an ideal situation, the intersection is basically just one of these circles. And since the Dice coefficient divides by the predicted plus the ground truth, you multiply by 2 so that you get a metrics that range from 0 to 1, okay? So basically 0 means you're completely wrong. 1 means you're perfect. And by the way, if you get a 0, then you've done something right, because just by probability, some of them have to be right. And if you get 0 on this intersection over union, and assuming that you don't just have a bug in your program, then there's something deterministic going on there. So I'll just say, I once had a professor that gave a true-false test for the final exam, 50 questions, and basically you got 100 in the course if you got 100, and you got 100 in the course if you got 0. Because the only way to get 0 on a true-false exam is if you really know, if it's got a lot of questions, is if you really know the answers. Because otherwise, you couldn't possibly get every single one of them wrong. Okay, so it's the same idea. So you need an annotated test set to calculate the metrics, which I don't quite have yet, which is why I haven't actually calculated the metrics. And there are other metrics like precision, accuracy, etc. But those are better suited for classification problems, and these are very well suited for a semantic segmentation problem. So that's how you do that. Now, I'll just take a couple of minutes to say something about microscope images, because I know that most people probably do microscopy. So these are stem sections from those soybean plants, and we want to segment the stem sections to correlate that with productivity. And this is an example of a segmentation, right? There's pith and xylem and fibrous caps and cortex. And I got to tell you, I wouldn't have known any of these words except that I work with Van Allerting and she works with plants and we're collaborating. So I got to know something about plants. But the problem, and this is all done with classical segmentation, classical image processing. And then the problem is there's one more thing we want. And what we want is something called the secondary phloem. And that is the area between the fibrous caps and the xylem. And it turns out that that's not so easy to do, even though it looks sort of easy, because it turns out these fibrous caps do not always follow the contour of the xylem. And for various reasons, it turns out to be not so simple to do. And we're thinking of setting up machine learning to find this part, right? And but I just want to show you. So the classical problem that the classical approach I use doesn't work very well when the sections are damaged, because I depend on the circular morphology. But if you look at shallow machine learning, just look at this, just a little annotation, and look at that. That worked pretty well. But it thinks that the primary xylem is also cortex. But that's no problem, because I can use classical image processing to separate the things that are on the inside of the xylem from what's on the outside of the xylem. See, so I can combine the tools. And look how, and this just took a couple seconds to do what I worked, one summer for. Now look, it works also on broken sections. Okay, except that it thinks I've got pith on the outside here where it's broken, but no problem. Classical image processing to the rescue. So this is a nice example where shallow machine learning combined with some classical image processing can do quite a bit for you. Okay, so I don't want to, deep learning isn't the end all of everything. Okay, and here's an example where I can use my classical segmentation to create a label image in QuPath, because QuPath can interface with ImageJ regions of interest. And then I can save it, and then I can do a manual annotation of the secondary flow and then save it as a label image. Okay. So that's nice. I mean, that's a nice thing to do. I only thought about doing that after I prepared the first part of the talk. So then I tacked that on also. And I hope that now, so just a few minutes, I'll just summarize. Classical image processing can segment some plant issues very well. The machine learning allows one to use a large feature space to segment difficult cases. Deep learning can be used for even more difficult cases where the feature space is not obvious. And the classical image processing can clean up the output of machine learning and deep learning. A rich set of tools are available for machine learning, trainable Weka segmentation, Ilsastik, TensorFlow, PyTorch, mianalyzer for deep learning. I didn't have time to talk about microscopy image browser, but Google on it and check it out, because it also does deep learning, and as well as a lot of other things. And it runs under MATLAB, but it also has a standalone version. I haven't checked the standalone version, but it also has a free standalone version. And I really recommend you take a look at it. It'll be a real shout out to that. And I focused on the tools I used: ImageJ, Fiji, Ilsastik, QuPath, mianalyzer, and so on. But there are a lot of other tools available. You're going to hear a lot about Cell Profiler, for example, and there's no good reason why you wouldn't use that, except, I just happen to not. Many years ago when I was playing with it, it wasn't that Linux friendly, like 5 or 7 years ago or something. But by now that's probably all changed. So there are a lot of tools out there, a lot of tools. And I just showed you my journey, the journey I took. I hope that helped you. And just in the few minutes left, if there are some questions, I'll be happy to take them. I don't know how this works. There are additional sessions coming after mine, but if my session is separate from the others and people want to ask me questions that run over, I'll be happy to stay a little bit later and answer those questions also. So with that, I'll turn it over and see if there's any questions. And okay. All right. Are you able to unmute? I mean, I don't know. I see there's questions. Do I have to unmute you? Let me see if I can. Okay, wait a minute. I have to unmute. Okay, let me try to unmute you. I see there's a question, but I need to know how to do this. I was normally asked to unmute more. One moment. Let me try to get this. Is it alphabetical so I can, let's see. Jan, I'm trying to, here it is. Okay, so let's try this. Ask to unmute more. Let me try to make.
Yeah, I already. No, actually, I didn't have a question. I just wanted to thank you for the talk. So that was
okay. No problem. No problem. Okay, no, I see you are able to unmute. Good. Okay, so if there are any questions, that's fine. Thank you very much. If not, then again, thank you for listening.